Hi everyone, David Mala here. Today we're going to do something really cool. We're going to do linear regression in Python. We're going to do it in Jupyter Notebooks. As you can see right here, we're in Jupyter Notebooks. And we're going to be working with the air quality for Bangor Maine data set, which has things like SO2 and oxygen and hydrogen and nitrogen levels in the air. And we're going to look at the air quality levels. And primary our focus is going to be on SO2, sulfur dioxide levels, because obviously if it's too high, it smells like rotten eggs in the air. If it gets really high, it gets people sick. So we need to know that. And in Bangor, Maine, in the Maine area, they have a lot of agriculture and chemical plants. And so if the wind does not blow the air off to the coast, sometimes these levels of SO2 and other related compounds in the air can concentrate and get very smelly or very strong and unhealthy. All right, so first let's start off with what we're going to do here is we're going to import our libraries, right? So we got pandas, matplotlib, seaborn. You don't need this one of random. We're not going to use it in this one. I don't know why I have it in there, but that's fine. Then we have sklearn, and for sklearn, there's different components of it, so make sure you have the linear model, preprocessing, train test split, and RFE. If you do not have those, you'll find errors when you try and do the things we're going to do down below. So let's get started with this. So first we're going to load in our CSV file, right? So this is locally, and you can get this from there's several government websites that will have air quality data sets for you that you can use. And this one's a CSV, and we're going to load it with the pandas pd.read CSV. We put it in data 1. Make sure that this is important right here. See that little R right in front of this? When you import a CSV, a lot of times I run into an issue in Python where it's looking at this as a literal text or a string, and it can't find it because it sees it as that. So you need to go and use this R, which means this is a raw string, not a normal string, literal, and then it will find this your location of your file, and it'll find it once you put that little R in there. If I didn't, it'll give me errors saying fields 2 and 3 it can't find, whatever, something like that. Alright, so next what we're going to do is we're going to take this, once we put it in, we put in data 1, we're going to put it into a data frame. So we use pandas.pd.dataframe data 1. That takes that and puts that into a data frame, which is easier to work with. Then we want to look at our data frame. So df.head n equals 6 rows, and look, we got 0 through 5. So it's like an array. In Python, you will not get 1 through 6. You will get 0 through 5 for 6. That's the way it works. So in here you can see our data. We have date, time, month, nitrogen, oxygen, argon, CO2, CH4, which is carbon, O3, H, and SO2. This is the one we're going to be looking to predict right here, the SO2 levels. Now next, I want to be able to look at this data and see for my SO2, right, for this one right here, how is this distributed in this data? Is it skewed? Is it biased? Is it leaning to the left, leaning to the right? Is it a normal distribution? So what I do is I do plt plot.figure, and I want the size to be 10, 5. The reason why I don't have it as 10, 10 is it's too big of a square. It takes up too much space and doesn't look right. So this shows me everything I need to know, and then I put data frame, which is the DF, which is what I called up there, of SO2. I want that field from the data frame. Dot plot, and the kind is a histogram. See that right there? So I'm doing a histogram based on that right here. And I can see from that my frequency, and you can see right here from our data that most of the days fall in 0.4%. Now an interesting fact here is when you hit 0.75% and above, the air smells like rotten eggs. If you hit 0.85 and above, which is somewhere right around here, then it's very strong and people don't like to go outside and shop. So this whole process here we're doing was actually used in Bangor, Maine for a grocery chain to figure out why some days out of nowhere for no apparent reason people didn't like to shop. And we found out what it was that the levels of SO2 were above 0.8. And that made it so people didn't like the smell of the air outside. They didn't feel comfortable, they get headaches, and they didn't want to go shop. So this shows the distribution of the data, right? It's mostly around 0.4. It's not smelly. The people can go out and shop and do what they need to do those days. So next we're going to do is we're going to define the target, right? So we got our target is SO2 and the non-target learning variables, okay? So what we're going to do, and then we're going to drop any non-numeric fields, because anything that's non-numeric, so if I had a date field that's truly dates, not numbers like this, if I had a field that had descriptors in it, right, something like yellow, orange, brown, you can't have text in there. So what we're going to do is look at this. df equals df.drop. See that? So we're dropping from the data frame things that we don't need. So if you go back up here, time and month are basically useless because the month stays the same for the entire month. That doesn't need to be used to predict. Same with the time. Okay, that would kind of skew the numbers. So we're removing those, and any non-numeric fields also get removed too. Then what we do is we drop the SO2, okay, and the data frame SO2 becomes the target variable. So see how this goes into Y, and then X is our without the SO2 in it. See that? So we have X and Y right here, okay, and then we have the head, which is N equals 6. Okay, so by doing that, I'm listing again the top 6 rows of what I've done. Now, just because it says drop SO2 does not mean it's not going to list it here. This is the data frame. That's X that gets that drop. See that? And Y becomes SO2. Okay, and we'll use that in a minute. So Y is our dependent variable. X is everything else that we're going to use. Now, next we want to do is not everything in those rows of data, or those columns data, is going to be useful or have correlations or positive or negative correlations that we can use. So in this case, we're going to use the Pearson correlation function, which is CORR with 2 parentheses, and we're going to plot all correlations, right? So when you look at correlations, as they get closer to 1, they're strong. Anything above 0.5 is a strong correlation. Anything below it is a weak correlation to 0, where it's no correlation. Now you can also have negative correlation, so negative 0.5 to a negative 1.0 would be a very strong negative correlation. What that means is as SO2 levels go up, this one would go down and reflect to that. Okay, so what we're looking at here is we're going to plot the figure size of 9, 8. You can figure out what works best for you. For me, that would look best. And we're taking the df, the data frame from above, dot correlation function, like I told you, put in COR, and then we're going to make a heat map based off it, right? So we got sns.heatmap, core annotations equals true, cmap equals plot.cm, and I'm using red, yellow, blue. Okay, there's many different color combinations you can use. You can look them up as to what you should use in a heat map in Python, but in this case I use that so that way the low end is, for a negative correlation, shows the dark red, and the high end, which is what we're truly interested in, would be a blue to a light blue, right? So I've got these guys right here, and this is primarily what I'm going to be looking at. So then you hit plt.show, show the plot. If you don't hit that, you won't see the plot. Okay, so then out of that, we have these correlations, but what I want to do is I want to identify the positive correlations with the target variable. So I want them, I don't care if argon has a high correlation with CH4, that's not helpful. I want to see what is in reflect to SO2. So use target correlation, that's what I'm going to call it, equals the absolute of core of SO2, okay? And then what we've got is positive core target equals target correlation, which is this, of the target correlation greater than 0.5. So what I'm doing here is I'm filtering it to just be 0.5 or greater than 0.5, because anything less than that is a very minute correlation, okay? And then I'm going to go and print it just by using positive correlation target. And what it tells me down below is O3, H, and of course SO2 have a strong correlation with SO2. This doesn't matter because we already know we are dealing with SO2. So the O3 and the H are the ones that are most important, 0.77 and 0.74. Okay, so we want to see what their strength is between. So not only do we want to look at just that they have correlations to SO2, are they correlated to each other? Because if they're correlated to each other strongly, right, then I can remove one of them, and I should remove one of them and only use the other one. Okay, so that's what this one is right here. Print df O3H dot correlation. See that? So that's just with each other. See it right there? That's what I do. And it gives me O3, H, O3 and H. And I can see 0.78, 0.78. They're greater than 0.75%. See that? So they're 0.78, 0.785, 0.79, however you want to round it up. Okay, so they've got a very strong correlation to each other. So what that means is what? I'm going to keep one of them and remove the other one. So we're going to drop unnecessary columns, low correlations, but they're both strong. So I could drop them both, but they're strong enough that I'm just going to keep them both. So I could have dropped the H or the O3 in this case because they're strong, but they're not at 90 or 100. I'm going to keep them both. And so I've got them both here. And then what I'm going to do down here is I'm going to create a test and train variable using the test train split from the sklearn library put in above. So if you see here, you've got x underscore train, x test, y train, y test equals train test split. So we're bringing in the function of our data frame, y test size equals 0.25. See that? So what I'm doing is I'm splitting up. So I've got 25% in the test and 75% in the train, right? In the training set. So when I print this up and I print the x train.shape, y train.shape, and I print x test.shape and y test.shape, what I get is I get 681 in the train set and 227 in the test set. See how that works? Now what I want to do is I want to fit the linear regression model. This is the simplest part of this. So LRM for linear regression model equals linear model dot linear regression function. See that right there? And then the LRM model, okay, equals LRM fit. See that? Of X train and Y train. See how that works? Okay. It takes the LRM right here, dot fit of this, gives me the model. And then the predictions are LRM dot predict of the X test, right? Because I don't want to predict the Y test, right? Because the Y was the SO2. I want to predict based on the others, right? So then what I do is I go down here and I have LRM predictions 0 through 10. In this case, what I'm doing is I'm just showing you the first 10 of these predictions. See them right there? So you quickly look at them and say, oh, hey, are they within scope? Are they within? Do they make sense? Remember above I showed you the histogram? Let's go back up there. And there's a reason why I did this. See how 0.4 is the middle? Okay, and everything happens between 0.2 and 0.6 for little bits. So if we go back down here, look at that. Everything's 0.4, 0.4, 0.42, 0.38, 0.24. They're within, it makes sense, okay? Just a quick look at it. Then what I want to do is I'll plot the predictions with a scatter plot, right? So what I'm going to do here is plot.scatter, y test, and plot.title, right here, plot of predicted versus actual values. See that right there? These are just the titles and the labels here. So the most important part's this right here, the scatter of y test LRM predictions. See that right there? Okay. And when you run this, you'll end up with a plot like this based on the data that you're using. So in this case, you can see here, just we were showing you earlier, is an awful lot of them around 0.4, right? But they do go, and there's kind of a line almost to it right here, starting down here and going up here, pretty much. So they're pretty congruent with each other, which is going to give me a high accuracy based on this, and a bunch in the middle, right? So if I were to do the score on this, right, so score, print the score of the LRM model dot score of X test, Y test, see how we do that? Ends up with a score of 0.707, which you multiply by 100, you get 71%, basically is what is our score. For linear regression, that's pretty good. And it also depends on your data, remember that, okay? So this is highly variant data, so it's not like you have patterns of up and patterns of down. The levels can change based on wind, can be changed based on weather, rain, all kinds of things can affect the levels of SO2 in the air, or emissions from agriculture or chemical plants. So once we have that, then we can print our predictions. It's very simple, just print predictions, right? Because we've already got the predictions right here right here. We've got our predictions, right? So we're going to print the predictions, right? So print predictions, type predictions, right here. So that gives me all of our predictions, okay? Then what we want to do is we want to add the predictions, actuals, and predictors, non-dependent variables, into a single data frame for comparison. Makes it easier that way to look at them, right? So right now you have the predictions are in predictions, right? And the SO2 actuals are in the Y test, remember that? And then everything else is in the X underscore test. So we want to combine them together. So we got as DF2, instead of using DF, we're going to use a data frame 2 is what I'm calling it here. We're going to put the panda.data frame of X tests, because if you use X test by itself, it's not a data frame, right? So we're going to put it into a data frame. And then we've got the SO2 actuals are the Y test. We're going to put them in right here, just so data frame 2. You got the brackets, and then we're going to call it SO2 actuals, and then we're going to do the same with predictions, and we're going to call it SO2 predictions. See that right there? It all goes into data frame 2, and then when I call in the head of it, I bring in, which is n equals 6 in this case, I bring in the top 6. It shows me the O3 level, the H level, the SO2 actuals, and the SO2 predictions, so I could actually go and see, well, how far are they off? If I wanted to compare on a daily basis, I could. And if I want to see all of them this way, all I have to do is use this code right here. We're using data frame 2, the 2CSV, TO underscore CSV. Remember, again, you got to have that R in there. If you don't have that R, you'll have the same errors you had above. Python does not like to use string text like this, but if you use the R, it makes it raw data, and then it goes in there and sees, you know, all of the folders it has to go through, and then your file that you want to save it as in this case, or up above the file you want to load in as. So we're saving as this dash results.csv, and that's basically how that works. So I just took you from beginning to end and showed you all the code of how we go and take a data set of air quality levels, right? Different compounds in the air. We loaded in the libraries. We loaded in the data set. We did a I quickly showed with the head command the top 6 rows. You could see what was in there. Then we went through and determined our dependent variable. We did a histogram on it to quickly see how this data is shaped, formed, you know, the distribution of it. And we needed that for later on. Then we defined our target variable and our removed any non-numeric fields, determined our learning variables. Learning variables went in X, the dependent went in Y. Then we showed it to you again. And then we did our correlations on that so we could determine any positive strong correlations, which we did with O3 and H. Now, down here we also determined that they're strong to each other, but they're not huge, or not 0.9 and above. So in this case, it's up to you. You could remove one and leave one. I decided to leave them both. Then you could drop. I showed you the code here. If you wanted to drop the other, columns that you don't need, use df.drop. And then I showed you what was left and we're done. Obviously, we have the SO2s gone because you don't want to leave that in there because it's a 1-to-1, very strong correlation. It's going to skew your results and give you false, thoughts that you're going to have some really accurate, 99%, 100% accurate data when you're not. So then we created the test and train variables using the test train split function. And then once we did that, we split them up to 75% train, 25% test. Then we built our model, our linear model with the LRM, or linear model.linear regression function. Then we got our predictions based off that. Then once we had the predictions, we created a scatter plot based off of the predictions backed up to the actual values. So as you can see in this graph right here, we've got actual values and predicted values. How close were we? And you can kind of basically see there's a line. This is going to be fairly accurate. And then we've got our score. We wanted to print the score. So not only would you see the line, or the possibility of a line go through here, we also want to get our score on it. So we use the score right here like this of the LRM model.score function, and we end up with about 71%, 70.7%. Then we printed our predictions. Then we were done with that. We wanted to put them all back together, right? Because there are 3 different forms right here. So we've got the X test, which we want to put that into a data frame. So we create a data frame. Then we bring in the Y test row, call it SO2 actuals, and then we bring in the predictions and call it SO2 predictions. So we've got them all right here, just like this. This is just the head of it, the top 6 rows. And then on top of that, then we dump it out to a CSV file by using the toCSV function and R. Make sure you use R for the raw data. So that's how you do linear regression in Python from beginning to end on air quality levels in Bangor, Maine. It's pretty cool how we were able to predict the actual SO2 levels. We could have predicted other things in there. We could have predicted hydrogen levels, oxygen levels, anything else, but we wanted to predict SO2 because it's highly relevant here. And if the SO2 levels are too high, as explained earlier, it would make the air smell like rotten eggs or worse, and can make people not want to go out and shop or buy things. So I showed you how to do that every step of the way. It's pretty fun, interesting stuff. Please take a moment to subscribe, like, and share. Tell me what you like, tell me what you don't like. Give me a comment. Thanks again, and have a great day.